Hello everyone, today's presentation is going to be about precipitation kinetic analysis in a maraging 350 steel using KJMA and Austin-Rickett equations. My name is Leandro. This work was developed for me, Ronald Lesley Plaut, and Angelo Fernando Padilha. Maraging steels are a special class of steels that differ from conventional steels due to the precipitation hardening mechanism induced by alloying elements, which promotes the formation of intermetallic phases in a martensitic phase supersaturated in the alloying elements during the age treatment. Precipitation in maraging steels that involves the nucleation growth of several phases, as well morphological changes of the precipitates during age. The S and omega phases are formed between 400 and 450, whilst at temperatures around 500 Celsius degree, and for longer age times, the Ni3T, Ni3 mole, Fe2 mole, Fe7 mole 6 phases are formed. The Ni3T phase presents a ellipsoidal morphology, and the Ni3 mole phase has a needle-like morphology, while the F2 mole and F7 mole phases have a spheroidal morphology. The follow-up of the precipitation kinetics of samples submitted to aging in maraging steels has been performed mainly through resistivity and microhardness measurements. In previous works that have performed kinetic analysis using Kolmogorov, John Mel-Avram model, there are no studies about the comparative analysis of the KJMA model with Austin-Rickett model. Hence, the present study consisted of the comparative analysis between the cited models in the analysis of the kinetics of precipitation use micro hardness measurements in the maraging steels 350 steel. And for this, I have used the following methodology. Samples were prepared by cutting of 10 millimeters thickness from 350 maraging steel bars of 140 millimeters diameter supplied in the solution annealing condition. Table shows that maraging steels 350 are steel with additions of nickel, cobalt, molybdenum, and titanium. These elements promote the precipitation matrix supersaturated. Each sample was aged at 408, 520, 560, and 600 Celsius degree for different times in a muffled furnace. Hardness measurements were carried out using 1 kJF load and dwell time of 20 seconds. X-ray measurements were carried out in the as received condition using diffractometer expert probe. My structural investigations were carried out using an optical microscope Olympus and in a scanning electron microscopy Phi Quanta. Samples for sand were mechanically polished and were etched with nitro 2% reagents, while the samples for optical microscopy were etched with Villela reagent. These results as received condition. Figure 1 shows that the structure of maraging 350 steel in the as received condition. Chemical etching use Villela's reagent, revealed blocks and packaged batteries of lead martensite. X-ray diffractogram shows the studied maraging steel 350 presents a fully martensite microstructure considering the detection limit of about 1% for X-ray diffraction. During age, several precipitates could be formed in maraging steels. Figure 2 shows the presence of nanometrical cylindrical precipitate at 520 Celsius degree for 18 hours, probably Ni3T as a consequence of the precipitation reaction in the hardening of the martensite structure during age. Figure shows that the variation in microhardness in the samples follows the typical behavior of an aging curve with a peak hardness, a hardness step, and another step for softening. Obtaining the fraction transformed is essential for KJMA and Austin-Rickett models, which can be performed based upon microhardness data obtained from the aged samples present in Figure 3. Equation 1 shows how is calculated the fraction transform, which is estimated via microhardness measurements. H0 is the microhardness in the solution annealing condition. HT is the microhardness for a given age time at a fixed aging temperature T. Age max is the peak microhardness at an affixed aging temperature. Figure 4 shows the transformed fraction obtained from the microhardness data as function of time and the age temperature. Figure 4 illustrates that there is an acceleration in the precipitation kinetics with a temperature increase in a way that indicates that the precipitation is thermally activated. The model of KJMA commonly is used in the analysis of the phase transformation kinetics in pure metals and metallic alloys. Deduced in the independent researches between 30 and 40 decades by Kolmogorov, Johnson, Mel, and Avrami. Equation 2 shows the KJMA equation. F represents the fraction transformed. K is the kinetic constant of the reaction speed for a given fixed temperature. N is a constant known as the Avram exponent. The interpretation of the values of the N constant in the KJMA models leads to the identification of predominant mechanisms in reaction controlled by diffusion as present in Table 2. Hence, N constant indicates the possible mechanisms of the precipitation. For example, N constants equal to 1 could be attributed to growth of long cylinders with constant length. KJMA equation linearized obtained from KJMA is shown in the equation 3. Started from equation 3, a linear regression of the data related to the fraction transformed with KJMA model has been as shown in the Figure 5. Figure 5 illustrates that the linear regression adjusted well to the experimental data. Table 3 shows the values of the n constant of the KJMA with, with the interpretation of these constants based on previous works of Hughes and Padilha, Starkin, and Christian. Table 3 shows that the values of n constant of Avrami may change according to the age temperature. These values increase with elevation of temperature between 440 and 480. The possible and constant interpretation is the coalescence of very larger after impingement or growth of precipitation and on grain boundaries, while for 520 Celsius degree and constant is the growth of larger cylinders with when compared with the separation distance between them with zero nucleation rate. For 560 Celsius degree and constant interpretation is the precipitation on dislocation in the initial stages or growth of larger cylinders with when compared with the separation distance between them with zero nucleation rate. Due to the small spacing between the precipitates formed in the initial stages of aging, it's supposed that the impingement of the diffuse fields may influence the precipitation kinetics, as no comparative studies have been found relating these models in the kinetics of precipitation in maraging steels. The comparison between the models of KJMA and Austin-Rickett is opportune. Another kinetic equation was proposed by Austin and Rickett for analyzing the decomposition kinetics of austenite in steels back in 1939. Later, Lin and King and Stark suggest that the impingement could be implied that the transformed fraction follow the Austin-Rickett model currently is given by equation 4 F, K, and N present even sign of those shown in the KJMA equation. Equation 5 shows this model in the linearized form as a function of transformed fraction. Starting from equation 5, a graph has been obtained based on the results of the fraction transformed. Figure 6 also shows a good behavior of experimental data when compared with linear regression. Table 4 illustrates the Austin-Rickett model also presented a good correlation with experimental data. For 440, the possible and constant interpretation is the precipitation on dislocation in initial states. It also would be possible for the occurrence of coalescence of very larger plates after impingement or growth of precipitations on ground boundary. For 480 Celsius degree and constant interpretation is the growth of larger cylinders when compared with the separation distance between them with zero nucleation rate. For 520 and 560 Celsius degree and constant interpretation is the growth of all precipitation from small dimensions with zero nucleation rate or decreasing, hence a criterion to define the model most adequate to describe the precipitation kinetics of the maraging steel 350 would be the comparison of the possible interpretations of the values of the n constant of the KJMA and Austin-Rickett models with previous studies on the morphology, on the microstructural evolution of the precipitations of the maraging seals during. Table 5 summarizes the possible interpretations of the n constants for Austin-Rickett and KJMA models, comparing the microstructural observations carried out by other authors. Thus, a comparative analysis of the microstructural evolution of the precipitates performed by other authors presented in Table 5 shows that the interpretations for the Austin-Rickett model are closer to the microstructure observations performed by other authors than the KJMA model. For example, at 480 Celsius degree, microstructure observation of the other authors confirms the growth of ellipsoidal Ni3T precipitates and long Ni3-mole needle-like precipitates, while n constant interpretation for the KJMA is the coalescence of very large plates after impingement or growth of precipitations on grain boundary. However, n constant of Austin-Rickett equation predicts the growth of larger cylinders when compared with separation distance between them with zero nucleation rate, have a better agreement with microstructural changes observed by other authors. Having a better agreement with microstructural change observed by other authors. However, complementary measurements should be performed to confirm the morphology of the precipitations in material studied. All of leads to the conclusion that the analysis of the precipitation kinetics performed adjusting the experimental data to the models of KJMA and Austin-Rickett showed that they adjust well to these models with a correlation to close to 1. However, the interpretation of n constants obtained through the Austin-Rickett model showed that they have a better agreement with structural changes observed in the maraging shields from previous works than those estimated through the KJMA model. The interpretation of n constant using Austin-Rickett model allowed to establishing several states for the precipitation. In the first one, the precipitation occurs on dislocation at 440 Celsius degree, followed by growth of long and thin cylinders compared with distance that separates them at 408 Celsius degree, and finally by the growth of the precipitates starting from small size with zero nucleation rate, 520 and 560 Celsius degree. Despite the microhydrogenase being a well-known technique in metallurgy and being largely used, it's allows obtaining some outstanding new results relate to the parameters of the kinetic of precipitation, both for the KJMA and Austin-Rickett equations in a maraging 350 steel that show that microhydrogenase measurements can be useful in studies of the nature in maraging steels. The authors are grateful to CNPq and CTNSP. The references used in this work. Thank you for your attention.